Mahesh Kakde from the Indian Institute of Science in Bangalore, and he will be speaking about Ribet's lemma in the residually indistinguishable case.
Okay, thank you. And I thank the organizers for inviting me to talk here. It's always a pleasure to come to these nice lecture halls and lecture. So I'll be talking about Ribet's lemma. I'll not talk about the motivation for it, except maybe mention just orally, and then try to. So the first part of the talk itself will consist of the statement that I have in mind, and then the rest of the talk will be about sketch of this, sketching the proof of this theorem. Okay, so right. So often we have this situation where so the first slide will the first board will be very vague. Often we have kind of a situation where you have a Galois representation into GL2 of K, where K is the field of fraction of something, a ring. And we know that after choosing a stable lattice, T lattice, you can reduce it modulo maximal ideal of T. So T is a local ring. The semi-simplification of that is a direct sum of two characters, and we want non-trivial elements in sort of chi1, chi2 inverse if these are the two characters, chi1 and chi2. Okay, so Ribet's lemma gives you a method of constructing such non-trivial elements in this group. Okay, so that's the motivation. But let me quickly write down the theorem. So this is joint with Samit, Jesse Silliman, and Julia Wang. So what does this say? So T is a complete reduced Noetherian local ring. By the way, so again, this is a special case of a theorem that we prove. In the theorem that we actually prove, we don't assume reduced because it's kind of the motivation. Okay, so as I said, the motivation comes, I'll just say it orally, the motivation comes from trying to prove Brumer-Stark conjecture at P equal to 2. And after I state this theorem, I'll during the sketch of the proof, I'll tell you what goes wrong at P equal to 2 with the usual thing that we do away from P. And for that, we need to work with rings that are not reduced. So certain Hecke algebras that we use are not necessarily reduced. I is some ideal. So this will turn out to be the so-called reducibility ideal. G is a compact group. A is the total ring of fractions of T. Rho is a representation of G into GL2 of K. And of course, Ribet's lemma in other situations is for arbitrary dimensions. I don't know if whatever we do works in arbitrary dimensions or not. We haven't tried it at all. So hopefully it does, but I haven't thought about that. Such that, what are the hypotheses on rho? So first of all, the characteristic polynomial of rho is contained in, has coefficients in T. Okay, so a priori, of course, it needs to be only in K, but it's actually in this. And the characteristic polynomial, so this is, it splits as okay, let me stick to my, so I call it chi and psi. Modulo I. So the characteristic polynomial splits as the product of two linear factors where these things are given by two characters first. So chi and psi These are from G to T cross. These are just characters. Okay, so those are two hypotheses plus some more. So suppose one, for every projection, we need some sort of irreducibility hypothesis, right? I did not say anything about this. I need to say that it's irreducible, but in the following sense. So for every projection A onto a field, for a field A, the induced map, the induced representation from G to GL2 of K is irreducible. Okay. Maybe this is the only one. Okay. Then what's the conclusion? Then there exists a finitely generated T module, which I'll call M, and a surjective cohomology class, which I'll explain what it means, and the surjective cohomology class kappa in H1 G M chi psi inverse, such that the fitting ideal of M over the ring T, this is contained in I. Okay. Fine. So what does surjective cohomology class mean? I'll just say it in words. It means that if you take any cocycle representing this class, the image is the image of that cocycle is whole of M. That's all it means. Okay, so cocycle is a map from G to M, satisfies certain conditions, and that function, the image is whole of M. That's what surjective cohomology class means. And fitting ideal is well, later on I'll define what fitting ideal is. But all this is saying is that M is large enough. So the size of M is large. So you have two things, that it's surjective, but the size is also large. If you remove any one of these, then of course the theorem has no content. Okay. So that's what this situation is like. I'm constructing a class in here, which is non-trivial. Okay, so where does the residually indistinguishable come in? So these two characters, chi and psi, if they are congruent modulo M, then we are in the situation of residually indistinguishable. So what happens if they are not congruent modulo the maximal ideal of T? Sorry, this M is maximal ideal of T. If they are not congruent to each other modulo the maximal ideal of T, then it's easier to prove this theorem. So I'll just say that. So let M be the maximal ideal of T. So first assume, and I'll sketch proof in this case. So first assume that chi is not congruent to psi mod M. So what happens in this case? So in this case, okay, so to prove this theorem, there are two things I need to do. I need to construct a module M, and then I need to, construct a module M, construct a cohomology class, and then show that the module M is large enough. Construct a surjective cohomology class, and then show that the module M is large. So I'll give you construction of the class, the module in this case, and then construct the cohomology class for you. Okay, so in this case, fine. So I fix tau in G such that phi of tau is not congruent to psi of tau mod m. That's what it means to say that they are not congruent, right? Then rho of tau has two eigenvalues, right? Two distinct eigenvalues. The characteristic polynomial will have two distinct roots. I fix a basis of eigenvectors. And that's how I rigidify my representation. So this is the usual thing in Ribet's method that Ribet does and then Wiles does and so on. And I write rho of sigma to be A sigma, B sigma, C sigma, D sigma. So these are all in K a priori. But so what is the module? So I'll in this case I'll call the module B, as is the usual notation. So this is T submodule of K generated by B sigmas, such that sigma is in G. Yes, so it's a finitely generated T module because G is compact and the representation is continuous. Okay, so that's my, well, this will almost be my module B. I in fact have to take B mod IB to get my M. Nevertheless, so what do we know? We know that the trace of this representation is in T and the determinant is in T. So I know that A sigma plus D sigma, this is in T. And in fact, it's congruent to this modulo I. So this comes from hypothesis. So this is one. And then the second thing I need is A sigma tau plus, okay. So remember that sigma rho of tau, this is simply A tau, 0, 0, and D tau. And so using the fact that rho is a homomorphism, you get that this thing plus D sigma D tau, this is congruent to chi of sigma chi of tau plus psi of sigma psi of tau mod I. And because this chi tau and psi tau are not congruent modulo I, you can solve these and you can get that A sigma is in T, D sigma is in T, and in fact, so all this is kind of an exercise. Okay, I'm just writing things down. What you can prove modulo I, just solving some linear equations, you get. So that's what you get. And these are the steps that don't work at all when you don't have this hypothesis. Okay. So at P equal to 2, all you can show is that 2 times A sigma is in T and 2 times D sigma is in T. So when you try to prove Brumer-Stark using this kind of thing. And yeah, it's not, we don't know how to construct cohomology class this way. So that was the sticking point, and we couldn't do Brumer-Stark at P equal to 2 in the way that we did it for odd primes. Okay. All right. So this what is the cohomology class now? So let me write down the cohomology class here. So again, this is the usual thing that if you have seen Ribet's method, you would have seen this. B bar. So what is B bar? B bar of sigma is in B mod IB. So this is my M. This is my module M. And again, you can show that kappa is a cohomology class with coefficients in M, chi, psi inverse. So again, that's an exercise using these congruences here. Okay, so I have 2 of my 3 ingredients from the theorem. I have my M, I have my kappa. And just by the way this is defined, it is surjective because B is precisely the module generated by all the B sigmas. So this co-cycle representing my kappa. So this is co-cycle representing my kappa. That's just abuse of notation. It is surjective. And so the thing that I need to prove is that the thing about fitting ideal of B mod IB. Okay. But the way fitting ideals behave, so this is just a fact about fitting ideal. This is same as fitting ideal of B mod I. Which is so B is now you see B is a submodule of the total ring of fractions here, so which is reduced. So this is a faithful so then since B is a faithful E module, and hence we get that the fitting ideal of B mod IB, which is M, this is contained in I. Okay, so that's the proof. It's not very short, but it's not very hard either. Okay, so that's the proof in the case when chi is not congruent to psi modulo M. So this was in Maser-Wiles itself. Okay. Ribet did not need to use fitting ideals because he was just working mod P. But as soon as you go modulo higher powers of P, you need fitting ideals. Okay. So now the rest of the talk is about sketching a proof when chi is equal to psi modulo M. And so for simplicity, I'll just assume that both chi and psi are 1. It just notationally is simple, but so for simplicity, assume chi is equal to psi is just the trivial character. Okay, so there are, as I said, there are various steps. So step 1 or step 0 is just the construction of M. And here we saw that to construct M, you just use the B entry of your, once you rigidify your representation in a certain way, you just use the B entry. And I think this no longer suffices. So what we do is the following. So you extend your rho to a map from TG to M2 of K. Okay. And you let delta be the kernel of this augmentation map from TG to T. Okay. And you let M be rho of delta modulo rho of delta squared. So that's your finitely generated T module. Simple as that. So now we have to construct cohomology class with values in M. We have to show that the fitting ideal of M is contained in I. Okay, so those will be the next two things. And the second of those takes the most time. So constructing a cohomology class is not hard, especially since we have assumed that chi and psi are both 1. We just need a homomorphism from G into M, and we do this as follows. So step 2, let me write it as a lemma. So I define kappa from G to M as follows. So this is G going to rho of G minus the 2 by 2 identity matrix. Okay, so this is contained in rho of delta. So I look at its class in M, and one can show that this kappa gives a co-cycle in M. with values in M. Okay, so that's the lemma, which I'm not going to prove. This is just easy verification that it's a cocycle. And again, just by the way M is defined, this cocycle is surjective. Right? M is just generated by all the elements of the form G minus 1, where G is in capital G. So that's the augmentation. That's how the augmentation is generated. Okay? So kappa is a surjective cocycle. So our goal is to prove that fitting ideal over T of M is contained in. Okay? So some very explicit thing that I'm going to try to sketch a proof of. And at this point, maybe, yeah, I'll tell you what fitting ideal is. Okay, let me write down a couple of things. Just because we have assumed chi and psi are both 1, we can actually verify easily. A lot of things that I'm saying we can verify are actually easy to verify. Minus 1, this is in I, and trace of rho of G minus 2 is in I. In general, I'll have to take chi of sigma times psi of sigma in the first place, and then chi of sigma plus psi of sigma in the place of 2, and so on. So that's why it just notationally becomes much more complicated if I take general chi and psi. But whatever is going to come after this is conceptually it's not any easier than assuming that chi and psi are arbitrary. Okay. Right. So let me, so let M be generated by, let G1 up to GR be elements in G such that rho of GI minus this, which I'll denote by rho I. Okay, from now on. Rho sub I is rho of GI minus the 2 by 2 identity matrix. Generate M as a T module. Okay, so M is a finitely generated T module, and we can choose these things so that rho I's generate M. So there are R generators for M. Now, how do we define fitting ideal? You take a set of generators, you take a set of relations, write down a presentation of M, and that will give you some matrix over T, and you look at the ideal generated by all maximal minors of this matrix. Okay, and that's the fitting ideal. So in this particular case, I'll say what the fitting ideal will be. So these are the generators, and there will be some relations. So relations will be of two types. Summation epsilon I, rho I going from 1 to R is 0 in M. So this is for epsilon I in T. So these are some relations that will be there, but there's other kind of relation which comes from the fact that M is not rho of delta, it's rho of delta mod rho of delta squared. And so the second kinds of relation will be rho of I, rho of J. This is summation delta I J K, rho of K going from 1 to R, or again delta I J K in T. Okay, so I take these two kinds of relations, and so today we are going to ignore these. These are easy to handle, and I don't want to spend time on them. Today, ignore these. Of course, we do have to handle them, but they are easy to handle. That's not where the difficulty lies. It's in this kind of thing. So we'll just assume that these kind of relations don't exist for today. Okay, so I take this matrix D0, which is delta 1 1 1 up to delta 1, 1 R, delta 1, 2, 1, delta 1, 2 R, and so on up to delta R, R1, up to delta R, R, R. This is a R squared by R matrix. Okay, so this is the matrix giving presentation of M over T, and the fitting ideal of M is all, you take all R by R minors of D0, and that gives you the fitting ideal. So fitting ideal over T of M is the ideal generated by all R cross R minors of D0. You take all R by R submatrices of D0, and you take, so you choose any R rows of this, and you take determinant of that. That will give you R square, choose R numbers in T, and then you just elements of T, and you take the ideal generated by that. Right? That's the fitting ideal. Okay, so fine. So what do I? Yeah, okay. Maybe I'll tell you how to. So at this point, you can try to do this by hand, and you can say, okay, if can I choose arbitrary R rows from here, look at its determinant, and can I write it in terms of traces and determinants of row I, right? Because traces and determinants of those row I's, they are in I. So if I can write this determinant by hand in terms of these traces and determinants of row I's, I would get my result. That's what you try to do first, and it works for R equal to 1, it works for R equal to 2, it works even for R equal to 3. You're hopeful that it's all correct, but you can't find a general pattern. That's where you get stuck. At least we got stuck. So R equal to 3 was as far as we could go by hand. Let me show you what happens when R is equal to 1. So the relation you have is row 1 is delta 1, 1, 1, row 1. And even here you see it's not like I just write this down and it's clear. So you have A1. So you have A1, B1. So A1, B1, C1, and D1 are entries of row 1. This is delta 1, 1, 1. A1, B1, C1, D1. Right. So you compare the which entry do you compare? Yeah, you compare the B entry of this, and you get B1, A1 plus D1. This is delta 1, 1, 1 times B1. And because of this hypothesis that we had about rho being irreducible when you project it onto any field, it gives you that B is a non-zero divisor. So some hypothesis implies that B1 is a non-zero divisor in T. So we can cancel that, and we get delta 1, 1, 1 is A1 plus D1, which is just trace of row 1, and this is in R. So we have our theorem when R is equal to 1. Right? It's kind of nice and easy in this particular case when R is equal to 1. And I could spend next 10 minutes and try to do it even for R equal to 2 here, and it's not that involved. So yeah, but I'm not going to spend time on R equal to 2, where you can do it by hand. What happens, so here we just use trace of row 1. For R equal to 2, you have to use trace of row 1 and row 2 and determinant of row 1 and row 2. But as soon as you go to R equal to 3, just row 1, row 2, and row 3 are not enough. You also have to use traces of row 1 times row 2 or row 1 times row 3, etc. So it kind of gets more and more complicated, and it's not clear if there is any pattern that one can use. So we have to do something more involved. So before moving on, I mean, so what you do is you reduce, I mean, you interpret everything in terms of formal variables so that you forget about your t and whatever other relations that t gives you. But before doing that, let me give you some simplification of or some modification of this. So you replace d0 by d, again r square by r matrix, which is obtained by just changing your entries. So entries in D are these delta ijk's. So you change these entries in the following way. So if you have okay, let me stick to my notes. So let me, no, my D is so what you do is fix R by R, the matrix D of D0, and this is what I'm going to work with. And you get E by modifying entries of D as follows. And I'll tell you why we do this in a couple of minutes from now. So if it's delta ijj, then you replace this by delta ijj minus ai. If it's delta iji, then you replace it by delta iji minus dj, and other entries you leave them alone. So entries unchanged. Okay, so why do I do this? I do this because of the following. So you can verify. Again, it's not hard to verify that just by using this particular relation. Here I use the B relation, right? So similarly, I use the B relation in here. So using this star, you can get that E acted on B1 up to BR. This is just 0. And again, all these are, I mean, at least one of them is non-zero in each projection to a field. So this will imply that a determinant of the determinant of E is 0. Okay, so determinant so why is this useful? Well, I'll tell you in a minute why this is useful. But before moving forward, I want to change everything to formal variables, and I want to forget about my specific t and my specific k, etc. So R0 is just z delta ijk. So here, of course, I, j, and k, they vary between 1 and r. So there are r cubed variables like before. R1 is simply R0, and then I join AI, BI, CI, DI. So again, these are 4 R variables here. And then from D, I get a bold D, and from E, I get a bold E by just replacing the entries with their formal counterpart. So maybe I should also put a bold here or an underline here or something, but I'm not going to do that. Just leave the notation as it is. And there is of course a map from R1 to K, which is just taking the corresponding formal entry to the element in K that's denoted by the same symbol. I is a map from R1 to K, which is just taking delta ijk to delta ijk. So this is the formal variable. This is not AI b going to AI, etc. Okay, and well, in this situation, we don't necessarily have that determinant of E is 0, but our goal is to show the following. Our goal is to show that if you apply pi to determinant of D minus determinant of E, then this is contained in so okay, I will not explain this. So so this is what I want to show now. Right, but what so what our aim in this particular section on formal variables is we want to get rid of our K, we want to get rid of our I. We want to completely work on the formal side. So this statement is just kind of an intermediate statement that we had that comes from before, but I don't want pi or K to have anything to do with the statement that I want to come up with. So I want to have a statement that's completely on the formal side. And then we'll try to prove that. Okay. So, so we haven't taken into we haven't taken into account these relations on the formal side yet. So we'll just do that now. So let J in R1 be the ideal generated by 4R relations given by, so I can rho I rho J summation over K delta I J K rho K, K going from 1 to R. So these are 4R relations because each of them is a 2 by 2 matrix containing these formal variables AI, BI, CI, and DI. And so there are, each of this relation is actually 4 relations, and there are R of them, R square of them, and those are the 4 R square relations that generate the ideal J inside R1. Okay, so I take my R to be R1 mod J. And now we are more or less ready to kind of, a few more notations. So as I said, our goal eventually is to show that determinant of D, or now determinant of D minus determinant of E, can be written in terms of traces and determinants of these matrices rho i's, or any word that you can form using rho i's. Because anything that you take in M, its determinant or its trace is contained in I. So so that's our aim. So let's give that a name. So A1 is contained in R1. This is R0 subalgebra generated by traces and determinants of all matrices in the non-commuting Z algebra generated by row 1, row 2, and so on up to row R. Right? You take all possible words in this and then all possible Z linear combinations of those. Traces of those and determinants of those are in I. If you do this with not with the formal thing, but the actual thing in K, then so in the formal world, I'm just taking all the traces and determinants of all these things and taking the R0 subalgebra inside R1 generated by such things. Right? That's my A1. So our aim would be eventually to show that whatever we want is, I mean, this determinant of D minus determinant of A is actually contained inside A1. Well, that's not quite going to be true because we have to take into account these relations also. So A1 is not quite the object that we want. The object we want is the image of A1 in R. Okay. So that's my object. So that's a R0, again an R0 subalgebra of R1. So just the thing is the ideal generated by AAI, BI, CI, DI. It's 4 elements. This is inside R1, and you can okay, my notation is messy here. You can show that determinant of D minus determinant of E is actually in I1. Okay, so the reason is these two only differ by, you see, I have only changed things by AI and DIs, and by multilinearity of determinant, you can actually show that this difference of these two is actually in this ideal generated by A1, A2, AI, BI, CI, and DI. Okay. So this is one reason why we need this, why we introduce this E. It's needed here. Okay. And then the other thing you can show is when you this is contained in R. So of course, the image of A1 will be a subring, and so that will contain 1. That cannot be contained in I. But if you intersect it with I1, that thing is contained in I. Okay. So so we need to prove. So our goal now is finally we have a statement that's completely on the formal side. Image of determinant of D minus determinant of E in R, which remember is R1 mod J, is contained in A. Okay, if we can show that, then we are done. So this thing is generated by traces and determinants. So if we can show that, then we are done. Right. So how do we go about that? Should I say? So at this point, I need to use this rational cohomology. So I'm going to, well, not at this point. I mean, I just need to get a better description of A1 than as traces and determinants. And so if you look at conjugation action of GL2 on R1, so you take one matrix and then conjugate all the row i's with that one matrix, and you take the fixed part of that, that is what's going to give you the ring A1. So let me write some notation down that's useful later on, and then write down the result that I just said. So let G be GL2. This, and then B is the Borel. So XZ inverse. Right. So let me write this down. So G acts on R1 by simultaneous conjugation. So A, B, C, D acts by conjugation on A1, AI, BI, CI, DI, and then you extend the action. So that gives you action of this A on all these things, right? On AI, BI, and CI, DI, etc. So this is what is called a simultaneous conjugation action on everything. And then it's a result of De Concini, the old one from the 70s, and Rosecci, that if I look at R1 and fixed by G, this is exactly A1. Okay, so that's the result that I'm going to use. Fine. Okay, so but as I said, we are not quite working in R1, and in R1, unless you take these relationships into account, you cannot even get anything. I think the result won't be true. So we want to work in R1 mod J and look at the so the action does descend down to this, and we want to look at the action here. So this is R1 G. Right? So we want to prove that. So actually, what we want to do is to show that X, which is determinant of D minus determinant of E, is in the image of this map, right? This particular map. That is what we are after. And it's not enough to, this map in general is not surjective. So this map, this is not necessarily surjective. So even if you show that this X is fixed by G, that's not enough, which is actually not hard to show. This X will be fixed under the simultaneous conjugation, but that's not enough. Okay, so what we are going to do is, because this map is not surjective, we want to show that, so we want to show that, let beta be the, we need to show that X is in this, but furthermore, we need to show that it's in the image of this. So let beta be the image of X in H1 G J, right? So I'm using I'm taking J R1 R, and then I'm taking the long exact sequence. So this is rational cohomology, by the way. So these are it is called rational or Hochschild cohomology. Fine. So let beta be the image in here, and we want to show now our goal is that right. Our goal is to show that beta is 0. Then we'll know that X is in the image of this from the long exact sequence associated to this short exact sequence. Okay. Fine. So at least we have some statement that we can now, it's completely on the formal side and we can try to do something. But again, just doing it by hand is one gets stuck. And the following thing is a useful thing to know, which we didn't know for a while, and so we were stuck for a while. It's this theorem. I don't know if it has a name, but I can try to later on. I can try to give you motivation for why this should be true. So V is any G module. So it's a finitely generated Z module on which G acts. And if you take the Borel, which I haven't yet used, this is an isomorphism. For all I bigger than or equal to 1. Okay. So we can actually replace our H1 G J by H1 B J. Okay, so our goal is again int beta is 0 in H1 B J. And why is this useful? Because here you can actually do something by hand. Okay, once you just have Borel, you can actually do something by hand rather than with GL2. So that's the thing we kind of do by hand. So what do we actually do? Let me tell you. And I mean, earlier in the talk, I said that the B entries don't suffice, but they still play a more significant role than others. So even in the case R equal to 1, you just saw that we used B entry, right? B entry only. Okay, so what do we do? So now we can more or less work by hand, but we need one more trick. So you replace J by this J prime, which is so J prime is the ideal generated only by the B entries of these relations that we have. Okay, so only by the B entries of delta rho I, rho j is summation delta I j k rho k. Okay, so there are only R square relations, not 4 times R square, because I'm just using the row entries. And J prime is a B module, but it's not necessarily a G module. Okay, it is a B module. So maybe at this point I should clarify that the Borel I'm using is of lower triangular, is of lower triangular matrices. So that's why I can use the B entry, and the Borel acts on this. And so we use 2 facts about this, which is a very nice argument to prove these 2 things, but I don't have time to give that. Let me just say that. So one thing is beta is in the image of this map, which goes from H1B. So J prime is the is the ideal contained in J, right? So there's a map from H1 of J to J prime to H1 of J. So one is you kind of do something explicit and show that it's in this map, which I'll denote by I lower star. And then second is a very nice argument to show that I lower star is actually 0. So the 2 things together will tell you that that beta is 0, right? Because beta is in the image of the 0 map. And the way we prove this is you construct explicit resolution of J and J prime, and then prove something about that resolution to actually show that this thing is 0. Okay, I think I'll stop here. This one, yeah, I mean, it's so this is affine, and if you just look at the 0th thing, right? It's affine, and if you are looking for and G mod B is projective, so you get like maps from projective to affine, so it has to be constant, right? If it's constant on B, but that doesn't quite work, I think. There's some technicality about, so then these things are defined as using injective resolutions, and I think the technicality is that if you have injective G module and you restrict it to B, whether or not that's injective, I think that's, so there's some work to be done, even, I mean, but the basic idea, I think. I don't know. I haven't thought that far. I mean, yeah, I don't know. Yeah, I mean, we apply the theorem at p equal to 2 to prove Brumer-Stark at p equal to 2. Yes. So because you see, generally, I mean, so what you have is usually you want an extension of, let's say, the trivial character by an odd character. And so if you're away from p equal to 2, you can always use complex conjugation to say that your character is not congruent to the trivial character modulo p. But that's no longer true at p equal to 2. And so you are in this situation where they could residually be the same. And then in general, you need to use. Yeah, it's kind of more or less theorem. Yeah. No, I think it may be that, yeah. Right. Yeah, I mean, I think that sounds correct, but I'm not confident in saying anything to it.